Well, hello, everybody. This lesson is either lesson 0 or it's lesson 75. If you are watching this because it's lesson 0, then what you're about to see is a summary of how this next 74 lectures will proceed, not counting lesson 0, right? Everything between lesson 0 and lesson 75. Right? We're going to give a general outline of how that's all going to go. If this is lesson 75 for you, meaning you're watching this at the end of watching everything else, then this is a recap of how we proceeded with the intent of sort of integrating things. Because we went on a few things that might seem to be tributaries of thought and things that I don't believe are very much. I think everything in this class is necessary. So I don't see a lot of digressions, but after 75 lessons, if you watched all of them, you certainly need some kind of integration. So I don't know if this is lesson 0 for you. If it is, I really encourage you to get a separate textbook. This is not meant to be a solo class. You should have a good textbook that you like. There's so many out there. If you want some recommendations, just ask me in the comments. But, I certainly recommend for... The level of material in here is at the level of Wald, at the level of Meisner, Thorne, and Wheeler, at the level of, Chandrasekhar wrote a great book. These are all sort of classical intermediate to advanced texts. The more beginning to intermediate text is Dinverno. That's really good. I would stick with Dinverno. Dinverno is really good. The problem is Dinverno has the weaknesses that prompted some of this lecture, which is filling in the gaps. When Dinverno talks about a manifold, he doesn't do it enough because he can't. He can't write. His book could be 1,000 pages. I can. I have all the time in the world. I can do 75 lectures without batting an eye, and it costs you 0. I don't have to publish it. I don't have a publisher to make. I don't have to pick and choose, right? I can just put everything there. So if you were reading Dinverno and going through these lectures together, that would be pretty darn great, right? And every now and then you could pop into one of these two books, which are quite difficult in comparison. But that would be the way to go. Something like Dinverno or something similar, and then these lessons. So that's if you're lesson 0. If you're lesson 75 and you feel comfortable with what you've done, you should pull open these books now and start from the beginning. And you should feel like you can attack it. It still won't be easy, but that's the goal. The goal of all this is to make it so these books are accessible. And this book here, Meisner, Thorne, and Wheeler, that book looks really accessible, but it really isn't. It's actually pretty hard. It has this very comforting tone that guides you into the difficulty with a smile, but it's actually quite difficult. But anyway, the whole point of these lectures is to make it so both of these books are ultimately accessible with a certain amount of confidence. So good luck to you, lesson 0 people and lesson 75 people. Thank you very, very much. And please enjoy this summary or recap. All right, I'm going to attempt to do a mind map of how this course is viewing this subject, right? In some sense, I want to be able to say, okay, this is the intellectual process we're going to go down through to understand general relativity. So in some sense, we've got to start with topology. When I say in some sense, what I mean is this is not very rigorous. There's many pedagogical paths through this. And the goal of this course was always to be quite thorough. It's trying to strip off that layer of superficiality when it comes to certain subjects that are important, right? So that's the problem, right? There's like topology. Topology is a very important subject just in general, but for general relativity, it's actually pretty important that you understand enough topology. However, if you're learning this course as an undergraduate or a new graduate student, you're not going to take a class in topology, and this is going to leave like little gaps and problems in your thinking about how to proceed through the material, or you're going to feel like you're making too many assumptions, or you're getting cursory paragraphs at the beginning of textbooks or cursory chapters at the beginning of textbooks that aren't very fulfilling and can't be, because topology is a full, to get the core of what you need is a full semester course, right? I don't even know if a quarter would do it. You'd need 2 quarters or a full semester course to really kind of say, okay, I've got introductory basic topology down. It's not a hard subject, but it's so abstract. But it is kind of an important thing. So topology integrated with the theory of vector spaces, right? If you have those two down, then you can combine those two together to get really what is the starting point of the study of general relativity. And that starting point is the subject of manifolds. Those two ideas combined, vector spaces and topology, are pretty mandatory. You could argue calculus, of course, as well. I'm assuming everybody here knows their calculus through multivariable calculus very well. In some sense, I keep saying in some sense, but what I mean is literally. I usually believe everybody here knows a certain amount of complex analysis as well, real analysis, complex analysis. In fact, the only topology most people have comes from real analysis. But anyway, combining topology and vector spaces comes together to form manifolds. In the work on this channel at the Xylix project, this material here, this comes from the What is a Tensor lesson series. If you want to be solid on your foundation, what is a tensor series? What is a tensor? Our lecture series on that will get you there. It's a way to. It certainly will guide you through what you need to know about vector spaces. The lecture series, What is a Manifold, will cover this entire body of stuff. And I don't say it's comprehensive. I don't pretend to be comprehensive, but I'm definitely far more comprehensive in those materials than you'll get in most introductory general relativity books. So none of the lecture series we do here is a substitution for a good book and a good course, but it'll certainly tell you what you need to know, and it will also get you well underway. But anyway, the point is what is a tensor and what is a manifold covers this material. And that is sort of where we start in this class, right? In the general relativity class. The idea is that once you have a manifold and you add the idea of a connection, now you've created the bulk of differential geometry. Those two ideas, because manifolds can exist without connections. But when you add a connection to the manifold, you can now start talking about differential geometry, covariant derivatives, geodesics, the curvature tensor, the Weyl tensor, and the Ricci curvature as well. So all these things and a lot of other stuff all come together with differential geometry. And the first leg of this class covered all of these subjects quite systematically. The Weyl tensor is quite an advanced subject, and it's not that critical for understanding elementary general relativity. In fact, you don't need to know it at all. But it's hugely critical to understand intermediate and advanced stuff, especially the way space-times are categorized or classified. It's a critical idea. Of course, the Riemann curvature tensor is the daddy of all curvature tensors, and the Ricci scalar is critical for the physics, because this is where this is the heart of the Einstein equation. So adding this connection is like a really big deal. So then once you have differential geometry, then you can start thinking about physics, right? The stress energy tensor coming out of physics, informed by differential geometry, you could argue, hey, you know what? That's where the Einstein equation comes from. It's this combination of differential geometry and physical reasoning. And out of the Einstein connection comes, out of the Einstein equation comes the metric. The metric on the space-time is derived from the Einstein equation. And then with the metric and with differential geometry, you can add the equivalence principle, which is an absolutely critical idea. The idea of inertial motion, right? The idea of inertial motion basically tells us that geodesics are the paths of free-falling objects. So you need that idea geodesics exist on a manifold without the idea of inertial motion. This is all math, right? But inertial motion, the theory, understanding inertial motion and saying, hey, geodesics and inertial motion, they're tied together. That's what these two arrows are implying. The equivalence principle is there to tell us that, everything has to be, the equivalence principle helps us understand the idea of how the metric will connect with the connection. In other words, the equivalence principle binds the metric to the connection, right? So without that, you really don't have the foundational idea about how to blend these things together. The point being, I guess I could have had an arrow that goes, the stress energy tensor gives you this, and then there's a certain amount of circularity because this will give you the connection, right? And then the connection, though, once the connection is bound to this, you no longer have pure differential geometry, right? You have what I'm going to put here, right? The idea is this is a purely mathematical subject. As I've drawn it on this side, this is all just raw math. This is sort of raw physics over here. And this is the physics saying, hey, I'm going to use this piece of mathematics, this differential geometry, to model the real world. And that model is going to be tied. This mathematical idea is going to be tied to the physical model through the Einstein equation, through the metric. And this is binding the metric to the connection, which is what makes this model, which makes this mathematical structure model reality, right? So the equivalence principle really tells us how to do that binding. Inertial motion gives us the idea of geodesics, and what are you left with? You're left with space-time. Space-time is differential geometry being used to model the real world. So there's sort of the mind map. I guess I'm kind of feeling like it would be possible to do this, right? The connection enters into differential geometry through the metric, or the connection is tied to physics through the metric, right? Because we end up using the metric connection. Okay, so there's sort of a mind map of how this goes. Now, what did we actually cover in this course? If you're at the end of the course, this is what have you learned? If you're at the beginning of the course, this is what you will learn if you decide to go through each of these lessons. All right, so reviewing the course through this lens, what was our sequence of learning here? How did we bind all of this stuff together? Well, I'm just going through the lesson sequence here, right? I'm going back to the beginning, and lesson 2 was titled World Lines, right? So obviously early on, I was very interested in this idea of the connection between geodesics, the metric, and inertial motion, because that's what a world line is. So we started with that. And the logic was, hey, well, what are we trying to, this is sort of a practical approach in a sense. I'm not wedded to practical approaches, by the way, but the idea is, well, what are we doing here? Well, we want to be able to come up with a scientific theory that predicts the motion of things. Well, the motion of things in space-time under the influence of gravity is along world lines, right? And so that immediately binds these fundamental principles. I think the first thing we did is we took the metric of space-time, bound it to the connection through the notion of the equivalence principle in the inertial motion. That was probably lesson number 3 and 4. Probably lessons 3 and 4 captured what world lines meant. Lesson 5, we introduced the catalog of spacetimes, and we kind of got a general idea of what were the other side of things, right? So once we know what the metric is, we can calculate world lines. Looking at the catalog of spacetimes tells you the metric is the solution to this Einstein equation, and there's not that many of them that are known out there, but you can get this really cool article that covers just about every one of them. So I'm kind of showing two things, right? In the beginning, I'm saying, hey, we've got this issue of can we solve for world lines? And then there's this other issue of can we solve for the metric? And I kind of lay that out there. But we go really hard on the world lines for a while, right? Lessons 8, 9 are about the metric connection, covariant derivative, and parallelism. I talk about the different kinds of notation, right, in lessons 10 and 11. And in this section, those two lessons, and then forever thereafter, we use component notation and coordinate-free notation together. The intent being that one of my goals, I love notation. I love doing different kinds of notation, and I love going through different books and comparing the notation. It's like the least physically interesting and the least possible intellectually interesting exercise for some reason I enjoy. But anyway, I do talk a lot about this, and the intent here is not to bore you and mix notations just to confuse you. The point is I want to force people who watch this to go through the exercise of distinguishing between these two kinds of notation. First of all, different books out there will use them both, so you need to know them both if you have any interest in using a real book, and you should be, right? This course is really just an assist, like a service road to a highway. The highway is some real book out there, and this is just an assist. But in order to be able to choose what book you want, I want you to understand both of these things. And I go through, sometimes I even do a lecture entirely component, and then I do it entirely coordinate-free. So we really get to the bottom of that, and that's for the point of clearing things up that cause real confusion just for students. Then we continue to talk about parallel transport for lesson 12, lesson 13 again. Lessons 14 and 15, we're talking about covariant derivatives. All of those ideas are in order to calculate geodesics. If you don't understand the covariant derivative, you can't understand geodesics, right? So we're digging into that. We talk about the metric connection again, because now we know once you can calculate geodesics with any connection, but understanding how to calculate it using the metric connection, that requires us an additional level of specificity. And it's critical because without the metric, to force the connection to be the metric connection, you can never really have a space-time. So we talk about that. That's down in lesson 16. Then in lesson 17, I do our first kind of significant diversion into topics that are less important, meaning topics that most introductory books certainly avoid, and that's the idea of torsion. And I like it because it really digs into the notation exercise. To understand torsion, you're going to be dealing with indexed gymnastics at its highest level, right? Plus, it is fascinating to see how torsion doesn't really affect the geodesics. If you have a space-time with torsion, the geodesics are actually the same. That was fascinating to me when I learned it. And the other reason I do these courses is things that I find interesting, I'm just going to assume you'd find interesting too. So I put it in there. So we talked about torsion. That was the next thing we discussed. So by the time we had torsion in hand, that basically told us what kind of metrics could work, what kind of connections could work. And then we really dug into the geodesic equation. Then we derived the geodesic equation. I don't know how many different ways I've done it. I think the first derivation we did way back in lesson 2, or maybe lesson 2 or 3, when we talked about the equivalence principle. But then we derived it again a couple different ways. And by the time we hit lesson 21, I think there were 4 lessons on the geodesic equation. And by the time we get to lesson 21, there's a very thorough coverage of geodesics there. For example, we talk about conformally related geodesics. I call them conformal geodesics, but I think it's when the metrics are conformally related. Well, first of all, we talk about what conformal metrics are, right? That's an important point, right? Two metrics have a relationship. They're a conformal relationship. That's an important idea because certain coordinate transformations can exploit this to simplify our intuition and our visualization of space-time through, say, Penrose diagrams and things like that. So I talk about conformal geodesics, and we show that conformal geodesics, the geodesics of conformally related metrics have the same shape, right? Are laid out in the same way in space-time. Well, they go through the same points in space-time. So that's kind of interesting. So we really, really dive into geodesics for several lectures, and we cover some pretty deep topics. And we finally surface from that stuff. Well, we surface from the theoretical part of it, and we then move into calculating the geodesic equations, solving the geodesic equations for the Schwarzschild geometry. And I spend about 5 lectures on that, right? So we not only do we go through all this stuff about geodesics, but we solve it for the Schwarzschild geometry, and we see how it's elliptic equations is sort of what it ends up. You end up needing to use a lot of elliptic equations, and it's pretty cool. It's pretty cool. And that process all the way goes through lesson 32, right? Up to lesson 32. So there's about 10 lessons just on solving one space-time for geodesics. But we kind of go through it in pretty big detail. It ends on 32. We actually I plot some of the orbits, and 33, 34, and 35 is just a series of math breaks that are just, a lot of this is review. In fact, I have to do this review of classical central force problem to really understand the GR problem. You've got to be very solid on your classical central force problem. And I spend several lectures on that, and I actually attack it very deeply, I think. Well, deeply relative to how I learned it initially. Whenever I say something is deep, it's like deep for me, right? It's deep as I remember first learning it. So we review the classical central force problem, and then that sets us up in a position to interpret the geodesics of the Schwarzschild spacetime. Remember, whenever you say interpretation, right? I think I said this before. Interpretation, to be able to interpret something, is very different than having intuition, right? Intuition, that to me is basically fake, right? People who say they have an intuitive understanding of something, what they really mean is that somebody's showed them a picture about how to interpret something. Intuitive understanding, this sort of innate understanding, is not really, if you feel like you have an intuitive understanding of something, you probably haven't formally learned how to interpret it. And there's many ways of interpreting things, but one way is to look at for this kind of stuff, for general relativity and for quantum mechanics and quantum field theory, is you're kind of looking at the classical theory, and you're looking for the connection between the classical theory and the modern theory. Now, general relativity is a classical theory. Don't get me wrong. I'm aware of that. But it's a very modern classical theory. So you take the classical theory and you compare it with the modern classical theory. And through that, you can do this interpretation. So to understand the geodesics of the Schwarzschild spacetime, you want to have a really, really solid understanding of the geodesics of the Newtonian spacetime. And I spend a lot of time on that. So totally worth it, worth every penny of it. Do it, enjoy it, review it. And then finally, after we've done that, after we've sort of exhausted geodesics, now we move over here and we start thinking, can we study the Einstein equation? Now that we've learned everything we can do once we have a metric, let's talk about figuring out what the metric actually is. And the core subject here was curvature, right? Curvature. We have to understand about how we're going to define the Riemann tensor, right? How are we going to define this, and how are we going to use it? How do we understand it? And understanding curvature that goes on from lesson 36, 37, like lesson 36 to lesson 48, right? Well, at roughly an hour a lesson, they're coming in a little under an hour, but that's 12 hours of just curvature. That's a lot of curvature. Well, we'll see, a 1.5 times speed, it's not 12 hours. 1.5 times speed is 9 hours. That's 9 hours. If you're playing it at 1.5, which I'm sure anybody who's doing this, I can't fathom how you would get through this without going to 1.5 speed. But it's still 9 hours. But they're fascinating hours because we study the curvature tensor and all that it implies. We define it different ways. We use different notations to define it. Coordinate free. We use coordinate free notation. We use coordinate based notation. And even when we're done, even when you hit lesson 48, the next two lessons are about the Weyl tensor, C alpha, beta, delta, gamma, right? The Weyl tensor, and that's just interesting. So we talk about how to define the Weyl tensor, and we prove its construction. We actually kind of build the Weyl tensor. We don't talk too much about it. You could actually safely omit those two lectures. That would be lecture 48 and 49. And you wouldn't lose anything from the core essence of it. This could have been a topical lecture. I concede that a few things in here could have been pulled out and be made topical. It's hard to tell until you're in retrospect. I wasn't quite sure. Maybe I was going to go deeper into this or use this to talk about the nature of space-time. But I think that's the point, is later I want to do a topical lecture about how to classify space-times. And when we do that, you will definitely need to know what the Weyl tensor is. The Weyl tensor is like how you do that classification. So I think it does deserve a place in a basic course, because a topical course, you could have a topical course in the Weyl tensor, then you would need another topical course on the classification of space-time. But that second topical course would be dependent on the other topical course, and then it becomes like a mini course. So instead, I'm taking the Weyl tensor and I'm putting it in the main course, and then a topical course can come up about classifying space-time. Although classifying space-time is a hard subject, it involves a whole different basis system called the Penrose basis system, and that so it's inevitable that'll be a mini course anyway. So I don't think I really saved a lot there. But then moving on, we talk about starting at lesson 51. We then have to talk about the Ricci tensor and the curvature scalar, and we go through. Now this is a place where I really worked hard to help develop an interpretation of the Ricci tensor and the curvature scalar. We definitely got a good interpretation of the curvature tensor, right? That was geodesic deviation and the deviation of a vector moving around in a little loop, being parallel transported around a loop. So understanding the granddaddy actually was kind of easy, but interpreting its contractions and interpreting the contraction A, B, and R, that was actually quite difficult. And that took a lot more lectures than I expected. But boy, it was a very deep subject. We talked about the pullback and the push forward in there, which is interesting because the pullback and the push forward is something that I almost certainly should have talked about real early, somewhere in here, right? Like way back here. Manifolds. Once you have two manifolds, you have a pullback and a push forward if you have a map between two manifolds. So that's something we could have talked about way, way back here. The problem is if we talked about pullback and push forwards here, it's kind of an abstract thing. It's like we've just learned what a manifold is and we feel real smart. Now we're talking about the circumstance when we have two manifolds and a map between them, manifold Marshall and a manifold Neal, and now we have a map between them. And then from there flows all these interesting other relationships between the two manifolds, or between functions on functions on the manifold, between tensors in various tensor product spaces. All those connections are bound up through phi, right? You bind tensor, you bind the vector fields here are bound to vector fields here, or vectors here are bound to vectors here. Cotangent fields here are bound to cotangent fields here. Functions here are bound to functions here. It's a mess. But it seems like a very weird circumstance, right? Why do I have two manifolds and a map between them? There's not enough practical foundation to make it seem like a very important subject back here. But it becomes a very important subject when we start talking about the curvatures, right? When we start talking about understanding and interpreting these things, we need the pullback and push forward. So we talk a lot about that. Pull back and push forward. So we interpret all of these things. We finally get a good interpretation of these two. And then once we have a good interpretation of those two, we now study the Einstein tensor and we interpret the Einstein tensor. So we have a good mathematical interpretation of all of these things. Then from the Einstein tensor, we develop the Einstein equation, right? And then once we have the Einstein equation, we solve it for the Schwarzschild metric, right? And then that's where the course kind of ends. So it binds together. We worked our butt off to get the geodesics for the Schwarzschild metric, meaning knowing the metric, calculate the geodesics, and then by the end of the course, we sort of seal it all up by solving the Einstein equation for the metric. And this sort of brings a path of understanding that went, let's see, how did it go? It went, if you look at it like this, we kind of went this way, landed on geodesics, and then we went this way and landed at the metric. So we proceeded like this in the first part of the course, and then we proceeded like this in the second part of the course. Or I guess it's better to say we proceeded like this in the first part of the course, right? In other words, we assumed the metric, and then calculated everything else. And then in the second part of the course, what did we do? In the second part of the course, we went this way. We assumed the Einstein equation, and, well, then I guess we assumed the Einstein equation, then we calculated the space-time, like that, something like that. Anyway, there's a lot to do, but now we are set up for all of these great topics. What are the topics we should cover next? Well, the first four that kind of come to mind are these four. The Kerr spacetime is kind of cool because it's the next simplest spacetime. The problem is it's not, I don't think we can just work through the solution of it like we did with the Schwarzschild metric. But we can certainly talk about the Kerr spacetime from ab initio and look at a lot of its properties. That's probably best to do after we study Penrose diagrams, though. Penrose diagrams is a way to visualize spacetime in its entirety in a compact picture. It's called a compact coordinates because the entirety of a coordinate that can go from, say, the radial coordinate normally goes from 0 to infinity, right? That's not particularly compact. Well, it's not compact in a formal sense, right? A topological sense. But the idea of a compact coordinates is that the entirety of space-time can be pictured in a little box, or I guess a little box on its edge usually. But the point is that that's a really valuable thing to know. And it's also important for understanding a bunch of stuff because, a lot of papers work in compact coordinates to express their ideas. So it is kind of important this is actually an important subject. We did discuss, it was important enough that we actually discussed it in some detail in the early part of this course, but we didn't really push it to its full limit. So understanding Penrose diagrams would be first. Then using Penrose diagrams, it'd be fun to study the Kerr spacetime or all the different black hole spacetimes, right? The tetrad formalism we touched on that too in this course because we talked about the Riemann normal coordinates. So we did talk about this a little bit, but we didn't really talk about the full-blown thing. For example, the curvature tensor, alpha, beta, gamma, delta, right? That thing can be converted into the tetrad frame. And you can do all of this work in the tetrad frame using the tetrad formalism. And so, and indeed, often it's done that way. So if you're going to proceed to more advanced subjects, you'll have to learn it. The idea of stellar collapse to me is interesting. Like the goal of this lecture would be a full understanding of the statement, nothing could stop the collapse, right? No known physical force can stop the collapse to a singularity. Well, I'd like to work through that and explain, okay, why is that? Right? Well, what is the breaking point where no known force can stop the collapse of a star? So that's a good subject to cover. So there's others, but all of these we're now in a position to understand. I mean, if you went through all of these lectures, which, look, would be crazy, 73 plus hours, 75 plus hours, really. That's a lot of lectures, and presumably this isn't all the work, right? This is just, something you're doing while you're reading another book on the subject, right? Because there's not nearly enough here to really, there's no problems to solve, for example, like you would get in a normal textbook. But anyway, these are some of these topical things that would come up later. So if you're on the front end of this course, these are things you won't find, although I got to say, you will find some of it. You will find a little bit about compact coordinates, and you will find something about tetrad, and not just a trivial amount. Definitely a foothold in these subjects. But this is really sort of what we're doing here. We attack the geodesics through an aggressive study of differential geometry, and we really step down on it on the Schwarzschild geodesics, which is a really interesting subject. And then we just crush the stress energy tensor by really studying curvature, getting a good feeling for what this equation means, how to interpret this equation. See, I said good feeling on what it means. That's like code language for intuition, and I really don't like that word. What I mean is we've learned how to really interpret this in the context of differential geometry, what this thing is saying about certain geometric principles, and how it reduces in the Newtonian limit. Those things are what interpretation's all about. All right, so thank you for sticking with the lecture. We'll see you in the topical lectures. And if you're on the front end, if you're reading this as lecture 0, good luck and enjoy. And please comment below. I do try to respond to as many comments and questions as I can. The problem is I don't remember everything, right? If you say, hey, go back to lesson, I don't know, I'll just pick a number, 31. I have a little question about what's going on at timestamp 543. That's going to be tough for me, right? Because I have to go back. I don't know all of this stuff. I'm constantly learning, forgetting, relearning, forgetting. And if I haven't been using the detail that you're zeroing in on in the past, 6 months, I'm going to have to go back, rewatch it, remind myself what it was all about, get it down again, and then read your question, and then see why, how to answer your question. And frequently people are finding mistakes. They say, I think you made wrong. You said it wrong. You used the wrong word. You said you had a sign wrong here. And those are the hardest ones to track down because I got to get it right in my head without letting my own work confuse me. And then I have to validate the alleged mistake. And, 50% of the time it really is a mistake. The other 50, if somebody calls out a mistake, it almost always is. Sometimes people ask a question that belies a fundamental misunderstanding of something earlier, but I do have errors in here, right? And I try to correct them as I find them, or as people find them. So call them out if you see them.